In the last video, we calculated pH, assuming acids and bases completely ionized. But most acids and bases don't behave that way. They only partially ionize. That means we can't just take the negative log of the concentration anymore. In this video, I'll show you how to calculate pH using Ka and Kb, and how to work through ICE tables step by step. This is where acid-base chemistry starts to feel more like AP or college level work. A common way to show acid dissociation is representing the acid as HA. The H plus will represent the proton, and the A negative will be the anion, or the portion that's left over. And since water is a solvent, we're going to omit that entirely from this. All right, so Ka, this is the acid dissociation constant. If it's a large number, that means that it's a stronger acid. And if it's very, very small, that shows that it's a weak acid. So the size of the Ka determines or shows the strength. Same thing for Kb. Kb will be the base dissociation constant. So when we go to write this, we can say then that the Ka is equal to the concentration of the H plus times the concentration of the A negative divided by the concentration of the acid. Let's go ahead and jump in our first problem. So I have a 0.10 molar solution of formic acid, and its pH is measured at 2.38. So we're going to calculate the Ka for formic acid at this temperature. So to start with, let's just say that the formula here, I'm going to draw equilibrium size. Let's be AQ, of course. Will be H plus and HCOO negative. I know that the pH is equal to 2.38. Okay, if you remember, pH is equal to the negative log of the H plus concentration, and the H plus concentration is equal to 10 raised to the negative pH. So let's go ahead and get our H plus concentration here. That's going to be 10 raised to the negative 2.38. So my H plus concentration will equal 0.00417. Or I can say 4.17 times 10 to the negative third molar. Okay, let's do an ICE table based on this. Okay, initially I have a 0.1 molar solution. Initially I have 0 parts of these. All right, since my final H plus concentration is going to be 4.17 times 10 to the negative third, I'm going to round off to 4.2 times 10 to the negative third, so we can stick with our proper significant figures. So this value is going to be 4.2 times 10 to the negative third. This will be 4.2 times 10 to the negative third. So I'm adding. And I'm subtracting here 4.2 times 10 to the negative third. So at equilibrium, this will be 0.1 minus 4.2 times 10 to the negative third. So let's set this up as a Ka equation then. So Ka is going to equal 4.2 times 10 to the negative third. That's the H plus. The formate ion will also be 4.2 times 10 to the negative third. And the acid concentration will be 0.1 minus 4.2 times 10 to the negative third. All right, there's some rules that you can follow to help with the math. I generally drop the plus or minus if it's 3 or more powers of 10. Okay, well this is 0.1, this is 0.3, that's only 2 powers of 10. So we could probably drop it, but let's go through and check it with a calculator and we'll see if we can or not. Okay, let's try this on the calculator. All right, so the first thing I want to do is set up a fraction. And then we'll say, open parentheses, 4.2. I'm going to second comma, that says times 10 to the negative third. And close parentheses and square that. On the bottom, I'm going to put 0.1 minus 4.2 times 10 to the negative third. Okay, that gives me 1.84 times 10 to the negative fourth. Okay, let's go back. And this time, I'm going to take off the subtraction at the bottom. Let's see, let's just delete backwards. Okay, so that gives me 1.764 times 10 to the negative fourth. So they both round. If I go to two significant figures, 1/8, but I generally keep the addition and subtraction unless they're 3 powers of 10 or more. All right, so we got two answers. If we kept everything, we got 1.84 times 10 to the negative fourth. If we dropped the subtraction here, we got 1.764 times 10 to the negative fourth. But both of these will round to 1.8 times 10 to the negative fourth. So this will be our answer. Okay, on our next problem, we know that the Ka is equal to 4.9 times 10 to the negative 10th, which is a very small number, which means that it doesn't ionize very easily. We know that the Ka is equal to, on our equation here, we have HCN aqueous to produce H plus aqueous plus Cn negative aqueous. So I know that the Ka is going to equal the concentration of the H plus times the cyanide concentration over the acid. Okay, we're looking for the pH. So to find the pH, we must solve for the H plus concentration. Okay, let's do our ICE table. Okay, so initially I have 0.2, I have 0 and 0, minus x, because I have the same coefficient about this equation, plus x and plus x. So this will be 0.2 minus x, x, and x. All right, so we will have 4.9 times 10 to the negative 10 equals x times x divided by 0.2 minus x. Okay, this time I will definitely drop this because this is to the negative 10, this is to the negative 1. That's 9 powers of 10. So therefore, subtracting x from 0.2 is insignificant. So we can go ahead and just not do that. So let's go ahead and solve. So I'm going to cross multiply. So I have x squared. It's going to equal 4.9 times 10 to the negative 10 times 0.2. So that will give me 9.8 times 10 to the negative 11. Take the square root of both sides. So x is equal to 9.99 times 10 to the negative 6, which is equal to the H plus concentration. Okay, the problem asked us to find the pH. All right, so the pH is going to be the negative log of 9.99 times 10 to the negative 6. So that gives me a pH equal to 5.00 for my final answer. Oftentimes, dealing with equilibriums, we need to do a quadratic equation. Here I'm showing you a simple program that I wrote on my TI-84 Plus, where I created a program called Quad, and then I chose these commands, as you can see here: clear home, display a title, display the equation, and then prompt you for 3 variables, A, B, and C. Then I'm calculating the plus and the minus versions, and I'm displaying them. I'll leave a video in the description to this video so it will help you to enter this if you don't know how. All right, so earlier in the last video, we did an ionization problem with strong acids and bases. So let's try one with weak acids and bases. All right, so I have HF, aqueous, okay, so it's going to form H plus and F negative, aqueous. I know the Ka here is 6.8 times 10 to the negative 4. And let's go ahead and populate an ice table here. So this is 0.1, 0, and 0, minus x, plus x, and plus x, 0.1 minus x, x and x. So my Ka is equal to my x times my x divided by 0.1 minus x. Okay, this is kind of borderline, so I'm going to keep my minus x in the denominator. Let's cross multiply. So I have x squared is equal to 6.8 times 10 to the negative 4 times 0.1 minus x. So that'll be 6.8 times 10 to the negative 5 minus 6.8 times 10 to the negative 4x. Let's put this in quadratic form. So x squared plus 6.8 times 10 to the negative 4x minus 6.8 times 10 to the negative 5 equals 0. I'm going to go ahead and solve this. All right, so my x squared is a coefficient of 1. My b will be 6.8 times 10 to the negative 4th. My c value will be 6.8 times 10 to the negative 5. And that was a negative. Let me insert a negative sign there. All right, so I get two answers. I can't have a negative answer here, so the answer must be 0.00791. So x is equal to 0.0079. Or I can say 7.9 times 10 to the negative 3rd. So let's calculate the ionization. Is equal to the H plus over the HA times 100. So we have 7.9 times 10 to the negative 3rd divided by 0.1 times 100. So my answer is going to be 7.9% ionization. Sometimes you'll be giving a diprotic acid, such as H2CO3. Since this is diprotic, I have to have two Kas. Ka1 is 4.3 times 10 to the negative 7. Ka2 is equal to 5.6 times 10 to the negative 11. All right, the Kas, they differ quite a bit. All right, I'm seeing here by a factor of 10 to the 4th power. Therefore, I'm going to say that K2 has little effect since it is so small compared to K1. So then we can do our ice table. We'll have H2CO3 aqueous, breaking it apart into H plus aqueous, plus HCO3 negative aqueous. All right, so our original concentration is 0.0037, 0 and 0, minus X plus X plus X, because they all have the same coefficient. So my Ka1 is 4.3 times 10 to the negative 7, x times x, x squared. And this is to the negative 1 2/3, that's the negative 3rd power. Negative 7, that's 4 powers of 10, so I'm pretty safe then by not doing this, okay? Because it's subtracting x is so small, it's not going to have an appreciable effect. So x squared is going to be equal to the product of those two numbers. So it'll be 4.3 times 10 to the negative 7 times 0.0037. So x squared is going to be equal to 1.59 times 10 to the negative 9. Taking the square root of both sides, I can have x is equal to 3.99. I'm going to round up to 4.0 times 10 to the negative 5th. So the pH then is equal to the negative log of the H plus, which is 4.0 times 10 to the negative 5. So the pH is going to be equal to 4.40. Okay, sometimes you're going to be asked to solve for CO3 2 negative in a problem like this. All right, well, what happens is, in the first, I would have H2CO3 All right, that's the first proton going away. Then my second one will be this equation. So I need to use K2 here. So in the previous problem, Ka2 was equal to 5.6 times 10 to the negative 11th power. Okay, so let's set up my ice table again. Okay, initially I had 4 times 10 to the negative 5th, because this is left over from the first reaction. All right, and also has some H plus from the first reaction. But I did not have any CO3 from the first reaction. So again, minus X plus X plus X. So I have 4 times 10 to the negative 5th minus X, 4 times 10 to the negative 5th plus X, and X. Okay, I'm assuming that X is going to be extremely small because my Ka value was to the negative 11th power here. And these are to the negative 5. So I'm going to not include those. So Ka 2 then will be equal to the H plus, the CO3 2 negative, so I'm going to say 5.6 times 10 to the negative 11 equals 4 times 10 to the negative 5th plus X times X over 4 times 10 to the minus 5th minus X. And I said I was going to discard these, so I'm going to discard this and this. Okay, notice that these two numbers cancel. So my answer for X then is going to be 5.6 times 10 to the negative 11 molar CO3 2 negative aqueous. Okay, so we're calculating the pH of a 0.15 molar solution of ammonia. And we're given a Kb value. So Kb, since this is a base, so just like Ka, Kb will be the products over the reactants. So I would have something that looks like ammonia. I'll go ahead and put the water here. It's a liquid. Gives me NH4 plus aqueous plus OH negative aqueous. So my Kb is going to be the NH4 ammonium ion concentration times my hydroxide concentration all over the ammonia concentration. Again, our old friendly ICE table. Okay, so nothing goes here. We started out with a 0.15. We have 0 here and here. Minus x plus x plus x. Okay, so minus 5 and negative 1. I see 4 powers of 10. So I have 4 powers of 10. I'm going to drop the minus x again. So I'm going to have 1.8 times 10 to negative 5 equals x squared over 0.15. X squared is going to equal 2.7 times 10 to the negative 6. And x is going to equal 0.00164. That's going to be molar hydroxide. We know that pH plus POH equals 14. So pH is equal to 14 minus the POH. So the pH is going to be 14 minus, open parentheses, the negative log of 0.00164. So the pH then is going to equal 11.21. At this point, you should be able to use Ka or Kb to calculate pH and work through ICE tables. These are the exact scales you'll need for buffers and titrations, which is where this topic really starts to come together. In the next video, we'll build on this and look at how buffers resist changes in pH and how to calculate their pH using the Henderson-Hasselbalch equation. If you're serious about mastering acid-base chemistries, that's the next step. So I'll see you there. Thank you for watching.